This program is a presentation of UCTV for educational and non-commercial use only.
So why even think about brain reward systems in a symposium on obesity and overeating and metabolism? Well, we heard fascinating things this morning from Dr. Johnson and Dr. Stanhope about how the metabolism of foods may be keyed into by the foods that we're eating, especially fructose, both intracellular metabolism and insulin systems. But we also heard from Dr. De La Pena that the foods we're eating have changed a bit over time, and so the rise in obesity may have something to do with how we are reacting to the foods that we live among today. And you know, a third reason comes maybe bottom up from the science, because in the last 10 years, I think the neuroscience of both hunger and satiety and of reward has changed. And what happened is that they've merged unexpectedly. They've grown together. It used to be so much a tradition that we could think about separately brain reward circuits quite separately from the systems and the metabolism of hunger and satiety and homeostasis cues. They're separate chapters in any neuroscience textbook or physiological psychology textbook. They're studied by different teams and laboratories traditionally, with a few exceptions, and the specialists have been traditionally different. But the brain never read our textbooks. And it's connected together. I think it's been doing all along. It's been connecting kind of to a remarkable degree, these two systems. And that's what's come up in the last 10 years, and I think we'll hear several bits about it today. They interact, food reward systems in the brain, with homeostatic systems of metabolism and appetite and hunger signaling in the brain. They're always interacting, the mesolimbic reward systems and cortical reward systems with hypothalamic homeostatic systems. These couple of diagrams are just a couple of examples pulled from the literature. This one here is from the late Dr. Ann Kelly, a marvelous neuroscientist of reward, who's basically trying to tell us in this little diagram a way in which hunger can make sugar taste better at a particular moment. She's sort of showing us a possible mechanism by which orexin signals in the hypothalamus can reach up to first the thalamus and then into the nucleus accumbens and turn on opioid systems of food pleasure to make the food taste better, to make the sweetness taste better at the moment of hunger. A circuit for that. Of course, there's dozens of potential circuits for that. And there's also opposite connections going from reward systems back down to hypothalamic systems. Can we suddenly feel hungrier when we encounter a cue for a delicious food just before lunch? Do we suddenly feel hungrier? Well, we may literally feel hungrier. And this diagram here is from Hans-Rudi Buteau at the University at Louisiana State University, who's showing us many of the interacting circuits by which cues in the brain cues for food rewards can trigger brain reward circuits to activate hypothalamic systems to turn on appetite and make foods taste better. So there's pulling and pushing going in both directions. Hunger and satiety changes the way we perceive food rewards at the moment. It actually changes the goodness, and I'd like to say a word or two about mechanisms for that. Why does food taste better when we're hungry, and why less good when we're full? And likewise, the reward system is reaching down into hypothalamic circuits of homeostasis and actually possibly modulating hunger and satiety states. So these are reasons to combine them. That there may be some cases in which binge eating or related eating disorders actually recruit slight dysfunctions that might be pinned on reward circuits in the brain, in which case reward systems might open a window to treatments of some forms of eating. But of course, that's only going to be some forms of eating and eating patterns and eating disorders. We may see many, many other cases in which mechanisms of the sort that we heard about today, metabolic differences in cellular metabolism, totally independent of reward circuits of the brain or eating patterns, are contributors. And maybe what we want to do is to be prepared that there won't be one route, even to what appears often to be a homogeneous condition. There may be multiple routes, and there's a little bit of evidence bubbling up that I'll mention in this brief time today. So in order to be in a better position to recognize when and when not food reward circuits might be involved in eating patterns of interest to us and how they we have to understand those circuits, and we have to understand how those circuits interact with homeostatic circuits. And thinking of brain reward circuits, maybe the place that I should start is with the notion that the brain may be making an almost non-intuitive separation of food reward into separate liking versus wanting aspects of the reward, which come on ordinarily together, so much so that we often can't tell them apart. It seems like two sides of the same coin. If you like a food, you want a food at that moment, and vice versa. But again, the brain may be choosing its own route and making a dissociation here. And I'd like to say a couple of things about that. I'd like to say first, what are some of the brain systems that can make food taste better when we're hungry, and which could be recruited in certain forms of eating pathologies to make foods taste better all the time for some individuals? And what are their mechanisms? This keys into the diagram that Ann Kelly provided us. What can make food actually taste nice? You know, the search for pleasure in the brain has been slightly frustrating for some of us in the reward field over the decades, because some of the best candidates that we had decades ago may not actually be mechanisms of pleasure in the brain, ranging from hypothalamic electrodes, so-called pleasure electrodes, to dopamine, the famous neurotransmitter of pleasure. But pleasure exists in our lives and in the brain. There are circuits for it, and so there are mechanisms for it. There's ways to approach, and I'll give you a couple candidates for that. To find a substrate for a mechanism that makes food more liked in natural moments of appetite, or in the laboratory when we key in and stimulate a piece of the brain, a system in the brain. What could do that? Well, one way of approaching this and asking, is a food liked at the moment, especially for researchers in my situation where many of the experiments must be done with animals to manipulate the brain, if we want to manipulate the brain, even painlessly, we need some way of measuring food pleasure in a person or an animal that doesn't tell us about it. And one route to that may have been provided in studies originally on human infants by Jacob Steiner in Israel at Haifa University decades ago, who looked at pleasure reactions of newborn human infants on the first day of life to the taste of sucrose. And this is an infant in Jacob Steiner's lab on the first day of life who's just had sugar water put on his tongue. Let me go back so we can see it a little more clearly. Just a drop of sugar put on the tongue, and what we see are sort of tongue protrusions, relaxed, licking of the lips. And then we see a rat looking from the below. We'll be looking up into its face. The rat's sitting on a transparent floor, and the rat will be having sugar water put into its mouth. And we'll see what it does. And then we'll see bitter reactions in both. So here's the infant, newborn, first day of life, first taste of sugar, those tongue protrusions. Here's the rat. We have to slow it down. That's too fast. The homology of movement means small creatures make faster movements. So here we can see some tongue protrusions and licking of the lips with the sugar coming into the mouth painlessly through oral cannula. And here's the infant showing bitterness. Oh, very different reaction. And maybe you get a sense. Gapes and head shakes. And here's the rat. The rat doesn't have a middle face musculature to scrunch the eyes and wrinkle the nose, but it can gape and head shake and flail its forelimbs and do a few more reactions like that. If you think you have a sense of whether the baby likes sugar but didn't like quinine, we can get something of an approach to the same sense in the rat by looking at these kinds of reactions, which change with taste, of course, but also with hunger and satiety. So hunger makes the sweet nicer with more positive reactions. They change with psychological manipulations of pleasantness. So learned taste aversions will make a sugary liking reaction into an aversive, bitter type disliking reaction, gapes to the sugar if it's been paired with illness in a taste aversion paradigm. And brain manipulations also can help us see some liking substrates. And the kinds of results that have come out of the search for mechanisms that can actually increase pleasure of tastes, of sweetnesses, make something nicer at this moment, as hunger could do naturally. These mechanisms have come up a collection of circuits in the brain, actually a collection of remarkably small, restricted, and fragile anatomical hotspots and specialized neurochemical systems in the brain. And I'll give you a couple of quick examples. It's a much more spindly and fragile system than we might have thought originally, the system for enhancing pleasure and making pleasures nicer. So for example, there'll be circuits from the nucleus accumbens that Ann Kelly was showing us down to the ventral pallidum, which is where the nucleus accumbens sends most of its outputs. And then those circuits get incorporated into larger circuits that go back to the cortex. And here's the first example, looking at opioids in the brain. Opioids are becoming synonymous with pleasure, or are synonymous with pleasure just as dopamine once was, but opioids have a better claim on it in certain locations in certain ways. So especially in the striatum and nucleus accumbens, the ventral striatum, here's a slice through it's a sideways sagittal slice through the brain, looking at the nucleus accumbens specifically, and actually even more specifically at the shell component of the nucleus accumbens, which is sort of wrapped around a wrapping of the nucleus accumbens, right in the middle of the brain. So this is a sideways view here. And we're seeing colors. It looks almost like a neuroimaging kind of colors, as though something were lighting up and coding pleasure, but that's not what this color map is. This is not a coding pleasure map. This is a causation of pleasure map. Because what's happening in this experiment, in these results, is tiny, painless microinjections of tiny, tiny droplets of opioid-stimulating drug, mu-opioid-stimulating drug, DAMGO, an agonist for mu-opioid receptors, is being made into the brain, and it's being made into the nucleus accumbens all over, down here where it's white, and down here and all around. And you can see there's just, and every time it's made, this little microinjection, the size of these little shapes that you see, the size is determined by how far that drug can activate neurons and make them genomically activated to make new proteins at that moment. That's what's giving us the size. But the color of the map is given by its psychological consequence, its behavioral consequence on the liking reactions to sugar of this rat as the sugar is being infused into its mouth. And wherever it's red or orangey red, that's where pleasure can be enhanced, where the liking reactions can be doubled or more than doubled by this opioid microinjection. It's mimicking hunger in a sense. It's keying in and making the taste more than twice as good at that moment. All else where it's not orange, like all throughout here where you're now seeing green, this measure of green is a totally different measure. This is elicitation of appetite. This is making the rat eat more, twice as much, 4 times as much, even more sometimes. And opioids, DAMGO, mu-opioid stimulation, all over the entire nucleus accumbens, all over regions stretching past the nucleus accumbens to the striatum, all over, it turns on appetite and makes the rat eat voraciously more. But it isn't enhancing the pleasure in all of those places. The green is going to stay here, and we'll just lay things on top. So the appetite induction, making the rats eat more, is there throughout. As we look at another effect, how about bitterness and making nasty things less nasty? How about making bitterness less nasty? Well, it turns out that some of the zones that make the rat eat more make nasty things like bitterness less nasty. How about making things nicer that are nice to begin with, like sugar? Well, this is the hot spot for liking enhancement. Only where it's orange here, which you can see is slightly smaller than the zone of making nasty things nice, or nasty things less nice, and much smaller than the zone of eating. Only in the hot spot, the red spot, is it doing all three things. Making food taste better, yes. Making nasty things less bad, yes. Making food more attractive to eat, yes. So we're kind of beginning to see a dissociation, a fragmentation of aspects of appetite, of liking and wanting, even coming out of opioids. And while it's synonymous to say that opioids in the nucleus accumbens are pleasure, actually opioids in most of the nucleus accumbens are not pleasure, are not generating enhancements of pleasure. They're generating appetite alone. It's only in the hot spot. So it's anatomically restricted. There are a couple of other neurochemical signals we already know that will turn on the same enhancements of food pleasure in that same hotspot. For example, natural marijuana in the brain, endocannabinoids like anandamide, if micro-injected into that same hotspot, have the same effect. They increase liking and wanting. It's not just the nucleus accumbens. As we said, it's also extending down into the ventral pallidum and larger circuits. I'll just give one quick example of a ventral pallidum hedonic hotspot. Here we've moved down to the ventral pallidum, the major target where the nucleus accumbens sends its signals to. And in that hotspot, opioid stimulation and endocannabinoid stimulation again enhance the pleasures of food, but also something else. And here's a hint to natural hunger, drawing on the theme from Ann Kelly. Orexin microinjections in the ventral pallidum also enhance the liking for food. And of course, orexin is a hypothalamic, lateral hypothalamic signal that might be activated in states of appetite, as also opioids and endocannabinoids are. But orexin is one step right into the homeostatic signal camp, a hypothalamic signal for hunger. And in the ventral pallidum, where some fibers from hypothalamus go and release the orexin, it can enhance hotspot. And anatomically, it's the same hotspot for orexin, for anandamide, and for opioids, all the same. So the brain is sort of restricting its pleasure intensifying mechanisms into little hotspots within larger structure. In the rat, each of these two hotspots is about a cubic millimeter in volume. In human brains, if it's exactly proportional to our larger body and brain size, it should be about a cubic centimeter each hotspot. These are tiny, tiny zones compared to the structures that they're in. And they operate with restricted neurochemical signals, just a few so far, opioids, endocannabinoid, orexins, and a couple of others. These hot spots, and there's a couple other hot spots in the brain stem and possibly in the orbitofrontal cortex that can generate increases in liking. And the last thing to say about this pleasure-generating mechanism is that it's fragile. The hot spots are scattered like islands in the brain, but they act as an archipelago that's all connected together. If you stimulate one hot spot for pleasure enhancement with a microinjection, it activates the other hotspots and causes them to become genomically activated to make new proteins and express phos in their neurons. And if you activate one hotspot with a microinjection to stimulate it, but you simultaneously suppress the other hotspot, you prevent the enhancement of pleasure. The circuit needs to activate the whole, and it needs unanimity between the hot spots to enhance the liking at that moment. The appetite for food can be somewhat separate. So food pleasure intensifications are kind of restricted in our brain. But much more of the brain is generating wanting for food. We've already seen examples in the opioid sort of sea of wanting that extends far beyond the tiny island of hedonic enhancement. You can stimulate, even for opioids, a form of wanting without liking, without increased matched liking for the same food. But other systems do it much more robustly, I think, and especially the original famous pleasure candidate in the brain, dopamine systems in the brain, may turn on wanting without liking. And I'd like to say a couple words about that, because that could be clinically important, too. Just a couple of examples to introduce this notion that brain mesolimbic dopamine might generate wanting for foods without necessarily enhancing the liking for foods. It's sort of a fragment of natural hunger psychologically that this system can do if it's by itself. original pleasure electrodes in the lateral hypothalamus that rats would work for and people would work for were also motivating electrodes. And in rats, the most common intense motivation is eat more when the electrode is on, implanted in the lateral hypothalamus. In humans, too, eating and drinking can be stimulated. Other things could be sex and other things. That's an old-fashioned way of activating the system. There's lots of modern ways of activating the system, and one, in a collaborative experiment with Xiaoji Zhang at the University of Chicago, talented molecular biologist, who's generated mutant mice who have extra dopamine in their mesolimbic, mesostriatal systems because of a knock, basically mimicking cocaine action on the brain through a genetic mutation. It's a knockdown of the dopamine transporter, which many of you know is like a molecular vacuum cleaner that normally sucks back dopamine into neurons that release it. Cocaine clogs this molecular transporter. It clogs the vacuum cleaner, so there's more dopamine left unvacuumed up out in the synapse. If you knock down this transporter molecule, it's like you're permanently on cocaine. You have a slightly broken vacuum cleaner, and so more dopamine stays out in the synapse. So this mouse has more dopamine, and it has enhanced motivation for food reward. Here's the electrode rat, and here's the mutant mouse. The electrode rat is eating more, over 3 times more, whenever its electrode is stimulating its mesolimbic system than when the electrode is off. And the mutant mice who have extra dopamine in a runway task to run for a sugary Fruit Loop reward, they run more avidly, they ignore distractions, they pursue their rewards, they'll work harder for their rewards than normal mice. And the question might rise then, do these dopamine-related activations that make rats eat more, do they make them eat more because they like the food more, as one might have thought from the original dopamine is food pleasure hypothesis? The answer is no, though. They don't, not at all. The electrode stimulation, when it's on or off, these are the positive liking reactions, and there's really not much of a change. What there is a massive change in are the disliking reactions, because when the stimulation electrode is on, the rats actually dislike, they behave as though they dislike even sugars when the electrode is on, compared to when they're off, even though they are eating 3 times more food when the electrode's on. So it's sort of an opposite change in wanting versus liking. And the mutant mice here, we just have the positive liking reactions for, there's 3 tastes: sweet, sweeter, and sweetest. Again, sweet, sweeter, and sweetest, concentrations of sucrose in water. And the sweeter tastes elicit more positive liking reactions, and you can see one group is higher than the other, but it's the wrong group. This blue group that's highest is the normal mice, the normal control mice. The ones who are lower in their liking reactions are these green mutant mice. The mutant mice don't eat or pursue food more because they like food more. They eat or pursue food more in spite of liking it less. And the electrode rats don't eat more because they like it more. They eat more despite actually disliking it more at the moment of stimulation. So psychologically, these things are being pulled apart, and it kind of exposes the nature of this wanting system. But it exposes the existence of a wanting system, but it doesn't tell us anything about the nature of the wanting system, its features that might be interesting in thinking about eating. So a feature or two. The main thing about this system is that it isn't just creating a drive internally like hunger. That's not the way the brain really works in its response to food rewards. What it's doing is increasing the impact of a perception of a food or a food cue at a particular moment in time. It's changing, actually changing in a sense. I think it's fair to say this, it's changing in a sense the perception of that food when the system gets activated to make that food more wanted. There's a synergy that happens. If this dopamine system is activated and a food cue is encountered simultaneously, there's a synergy, a massive elevation in wanting that can happen at this moment, but it requires both. Cues by themselves, do they trigger eating? Sure, but not always. Cues by themselves are not what are doing it. The brain state by itself is also not what's driving appetite. I'll give you an example. But combine the brain state of mesolimbic activation with a cue, and suddenly you have something special. So psychologically, and what this is going to mean is that cravings to eat acting through this system will come and go. They'll come with encounter to cues, but only if the cue is encountered in particular kinds of brain states. And they'll go when the cue, or when thinking vividly imagery about the cue goes. Just to give you an example of how this works, if you'll forgive me from drawing on a rat experiment, because here we can manipulate the system. This is cue-triggered wanting. It's really looking at the ability of cues. For us, maybe that's a food cue. For the rat, a sound that's been paired with sugar reliably in its history, a tone, beep, sugar, beep, sugar, beep, sugar. After a while, that beep becomes for the rat a little bit like this sight and other sights of food can be for us. And you can ask, does this cue evoke a motivation to work for food? Well, here's a rat who had learned once that if it pressed this lever, it could earn sugary pellets, little sugar pellets. And separately, it had learned that tone cue for food, Pavlovian cue. And today, for the first time, it's working away for food, but for the first time, we've turned off the sugar, so no sugar is coming, and it's getting disappointed as the half-hour test goes on. It's working less and less, going in extinction. But once in a while, that tone is played, and whenever that tone for sugar is played, it's a little bit like encountering a whiff of our favorite food as we approach lunch, a little peak in elevation of bursts of effort working while that cue is there. Then the cue goes away, the tone, it's only 30 seconds, it goes away, it goes down. If the tone comes back, there's another peak. The whole pattern goes down because the rat's extinguishing, it's disappointed, no sugar today, but wherever it is, the cue can pull it up from where it was. The real question, though, is what happens if you activate dopamine systems in the brain as all of this is going on? And the answer depends on what moments you're looking at. These lines down here that say baseline, CS and baseline, CS minus, they're looking at these horizontal bits of the test when there's no tone present. And basically, as you increase dopamine in the brain, this is a dose-response curve here, this horizontal axis. From 0 amphetamine in the brain, micro-injected in the nucleus accumbens, which would spill dopamine into the synapses in the nucleus accumbens. From 0 to increasing doses of amphetamine, if you're just looking at baseline, there's no effect. Activating dopamine in the brain doesn't change what the rat is doing. It's as though it's irrelevant that it has extra dopamine in its brain. And even when a non-food cue comes, a CS minus, the jargon, Pavlovian jargon for a tone that's never been paired with sugar, it's just been paired with nothing, there's not much effect. But when the tone comes, what the effect of dopamine is, in a dose-response way, is to amplify its ability to reach into the rat and pull up these cues. It's basically raising the height of these mountain peaks, but not at all changing the plateau it's sitting on. It means that that brain, in the absence of the cue, the rat looks normal. You can't tell it had amphetamine. But when the sugar cue comes, there's a sudden intensification, a massive intensification, more than, or roughly doubling, or sometimes more than doubling, the ability of that cue to trigger a strong desire or working efforts to obtain sugar at that moment. Well, dopamine. But, you know, other things will do the same. In stress, I'd like to say just a quick word about stress. We all have marvelous ways to explain why a person might eat more if they're feeling stressed. Marvelous work showing stress releases brain corticotropin releasing factor in the brain, including in the nucleus accumbens. And there's lots of reasons to think that we could eat more because stress makes us feel bad, and so we eat a tasty food to feel better, sort of hedonic self-medication. Hedonic self-medication. Marvelous work by Mary Dahlman showing evidence for this kind of mechanism. It does exist, and work by George Koob on brain systems to do it. That exists, but what I'd like to suggest, and I think Mary has also suggested, is, you know, there might be another route for stress to make us eat. It isn't the case that we have to feel bad in order for stress to make some people eat. The people who would eat in stress, perhaps the 30% who would, it isn't necessary that they feel bad. And there's two implications of that if it's true. One is that even happy stressors might trigger binge eating. You've get promoted, you've published a paper, you've had a success, you've won the lottery. These things might. The other implication, if this mechanism is the case, is that if a person is in distress, is in a hedonic, nasty state from stress, you can help them by raising their hedonic state and making the nastiness go away, but that may not solve their problem entirely. Is there any reason to actually believe this? Well, here's the reason. You just saw that experiment where dopamine increased the ability of the cue to reach in and trigger a pulse of wanting that only lasts a minute. It turns out that CRF in the nucleus accumbens does exactly the same thing. This is exactly the same experiment repeated. Exactly, everything is the same. The only difference is that in one microinjection is still amphetamine, this last one here, this column here, all the way to the right. But this one here and here are doses of CRF, not amphetamine, CRF in the nucleus accumbens, the same place where the amphetamine goes. And the effect of CRS is exactly the same as the effect of amphetamine in the nucleus accumbens. This is a case, it's a condition in which the rat is not at all distressed. The rat would work actually to obtain injections like amphetamine in its nucleus accumbens. And the CRF is acting in the same sort of way. It's just magnifying the ability of the cue to trigger a peak of wanting. And I should say that for both of these, there's no enhancement in liking. For either amphetamine or CRF, there's no enhancement of liking even if you can increase wanting. So it may simply say, as we mentioned, that even happy stresses may not be the dieter's friend for someone who's vulnerable to cues to trigger eating bouts. And likewise, ameliorating stress might not be the final pure solution to reducing stress-induced eating. So this gives us things to think about. Another feature, maybe the last feature I'll mention for incentive salience, to kind of, again, get this notion that it's transforming the perception and can really be intense to make us want particular things. It really does transform the perception even of the cue and make that cue attractive into a motivational magnet, attractive, riveting, good enough to eat. And just as an example of extreme case, in animal experiments, we can turn on this system and make even things that are totally inappropriate to eat, like a piece of metal that's just been paired with sugar as a Pavlovian cue. Not very promising as a luscious, mouth-watering cue, but let's see what happens if we activate this mesolimbic system here by targeting into the amygdala. This is a rat, let me pause. This is a rat who's learned that whenever this lever pops out, it predicts a sugar pellet's going to come in a dish 10 seconds later. And when this rat is called a sign tracker because it's going to find the lever so attractive that it's going to eat it. And then we'll see a second later a second rat who the lever triggers, and for this second rat, we'll see when the lever triggers the intense desire, it's directed at the metal food dish called the goal tracker. So let me just see this here. There we go. So the lever comes out and the rat goes to that lever, and there's what it does. It starts to gnaw on that lever, that sugar cue, with this activated brain system. And here's a second rat. It'll go to the metal dish. There's nothing in the dish at this moment, but when the cue comes, the rat goes to the dish and just nibbles and sniffs and gnaws and licks at that dish, this cue-triggered wanting potentiated by it. Of course, this is not, the point of this is simply that if such an unpromising cue as a piece of metal can be made so attractive through a few simple manipulations, think what can be done to real foods in our world if any kind of condition could even, in a weak way, tap into those same things. If it could be tapped into, there's a notion provided by my colleague Terry Robinson that if you could amplify dopamine and mesolimbic systems, these systems of wanting, if you could do that, you'd leave a person vulnerable to increasing wanting and wanting the more the system got activated, even if the pleasure of something went down. This has been applied to drug addiction as an incentive sensitization model of drug addiction, basically a means to make a person want drugs, even if they don't like the drugs. In binge eating, well, in drug addiction, it can happen because drugs don't only activate dopamine systems, they permanently change them in some individuals into a state of hyper-reactivity. So the systems can be re-triggered into extra activation in a permanent sort of manner that can last years. And now there are suggestions from Bart Hobel's and others' lab that maybe some kinds of eating experiences, especially dieting and overeating cycles, may induce neural sensitization that might produce a similar kind of thing. In addiction, it's cues like drugs that trigger it. If there's neural sensitization in eating disorders, it would be cues like that. But all of this is really just tapping in to a natural mechanism that's in all of us, cues for rewards that have activated human mesolimbic systems in brain neuroimaging experiments, and all of these kinds of cues will do that. That's what taps in. But if you did it to a higher degree in a system that was hyper-reactive, the intensity of those cue-triggered urges could dwarf the ones that most of us experience, and that's really the notion. Very last thing to say, and I think especially it has to be addressed for an eating-related audience, which is a natural skepticism that none of this should be true, based on what anybody who's worked with overeating and thinks about dieting drugs and such knows, because there are very inconvenient facts for what I've just told you. I'll just mention 3. One very inconvenient fact is, as I've said, dopamine is sort of a wanting system in the brain, mesolimbic wanting, but actually, many of you know, some of the most successful dieting agents have been amphetamine and then amphetamine-type drugs that aren't addictive but still promote dopamine, and yet they typically suppress appetite. How can that be true? How can what I said be true, given that that's a fact? Secondly, many antipsychotic drugs, such as given to people with schizophrenia, that are blockers of dopamine receptors, neuroleptic drugs block dopamine D2 receptors, yet they can produce gain in body weight in some people. How can what I've said be true, given that? And finally, many of you may know that dopamine D2 receptors have been found in a number of studies to be reduced in people and in animals who are overweight. And I think we may hear more about that. So those are problems. I'll just mention in a minute a couple of potential routes that might provide ways to resolve this. The first paradox is that amphetamine and dieting drugs typically do promote dopamine release. But 2 things to note about that. Most of those drugs also typically promote norepinephrine release. The drugs are taken systemically, so they're acting all over the brain, and especially in the hypothalamus, especially in the medial hypothalamus, norepinephrine acting particularly on alpha-1 receptors may suppress appetite very, very potently. People who take amphetamine or other dieting drugs are activating that. The wanting system we've been talking about is to the nucleus accumbens and striatum, related targets, but the hypothalamus is very different. And finally, in the hypothalamus, even dopamine may suppress eating. It's not that dopamine is a wanting transmitter all over the brain. Dopamine does different things at different structures and even at different concentrations in the same structure. The second paradox was that people can gain weight if they're given dopamine blockade. How can that be true? Well, I think it's fair to say that most of the gain in weight in the last 10 years from neuroleptics is now being assigned not to dopamine blockade, even though the drugs are blocking dopamine receptors, but rather to other receptors that the same drugs are also blocking, especially serotonin 1A and 2C receptors in the hypothalamus. There's serotonin modulation, and histamine receptors, H1 receptors, that are also in the hypothalamus. So it may be that one can, at a receptor level, pull apart the weight gain versus other effects. And the very last thing, it certainly is the case in humans and animals, maybe best known through the work of Neurovocal on humans, that people who are either drug addicts or are obese, heavily obese, may have reduced levels of dopamine receptor binding in their brain. Radioactive labeled drug that blocks dopamine, that binds to dopamine receptors placed in may show us less binding in these kinds of studies. And that's given rise to the idea that they have less food pleasure, going by the old notion that dopamine was pleasure, and to the corollary idea that if food and everything is less pleasant, maybe such a person would eat more in sort of a chase attempt to capture back the original level of pleasure. There's a certain logical plausibility to that. Of course, there is sort of a flag. I mean, as we heard from Dr. De La Pena today, as sugar increases, I mean, sugar is not a very good dieting aid. Giving people more sugary pleasure isn't quite an effective way to make them eat less. If the food outside is very, very tasty, we may eat more. Typically, we tend to eat more the more pleasant foods are, and rats are certainly the same. It's a little bit of a strangeness to posit that when food tastes less good, we eat more of that food. That's not actually an experimental kind of finding that would come out of the literature, and I don't think come out of the people. So this puzzle is sort of a logical flag. Could there be other explanations for this sort of thing? And there might be. It's basically an issue of chicken or egg. Are reduced dopamine receptors the chicken or the egg, the cause or the consequence of obesity? And it's just possible that dopamine D2 receptors can be pushed down on, at least in the binding patterns, either by excessive dopamine mesolimbic reward circuit activation or pushed down directly from homeostatic signals. Several bits of evidence that might suggest that in the last couple of years. I think we'll hear perhaps from Eric that as individuals gain weight, they may have a reduction in dopamine receptors binding. That would say the dopamine decrease is a consequence of weight gain rather than the cause. Eric will perhaps say whether he thinks that's the case. Conversely, in obese women who had bypass surgery that helped them to lose weight, as they did lose weight, there was a rise in dopamine receptors reported at least in one study by the Johns Hopkins group that I've seen so far. And finally, a study this last year in animals, an animal model, basically replicating the notion that as rats gain weight, because they're being given a diet of bacon and chocolate and other tasty foods, as they do gain weight on that palatable diet, their D2 receptors decline. So it's really just the notion that it could be a consequence rather than a cause. And finally, it's worth mentioning, as Ashley pointed out to a number of us in an email a couple weeks ago, that even Nora Volkov's group is now finding that obese binge eaters, when they're shown foods or tasting foods, they actually have higher dopamine release, not lower dopamine release, kind of more in keeping with a wanting notion. So I think it's on the table, this notion that mesolimbic systems might be a wanting for food. And it'll be a real question whether these basic mechanisms that we've talked about, whether they have clear applications to any cases of eating disorders. It's not for me to say, I don't study it, but I'll just mention as we stop these studies in passing, two of them, one by Carolyn Davis and her group in Canada, suggesting that some individuals who are obese and also binge eaters may carry a genetic signature for both dopamine and opioid genes that she suggests might lead them to have higher dopamine and opioid liking and wanting. Similarly, the Cambridge team, O'Reilly and Faruqi, have shown beautiful studies in genetically leptin-deficient humans who grow up within a few years constantly demanding food and overeating, and who have high activations in their nucleus accumbens to the site of food in imaging experiments. When they're given leptin replacement therapy, exogenous leptin, because they have a deficiency in coding leptin, it suppresses the nucleus accumbens activation when they've just eaten. It allows satiety, basically, perhaps to suppress these accumbens liking and wanting systems. It allows food in the stomach to do that when there's leptin there, suggesting a direct connection between one clinical condition and these mechanisms. Other people have suggested other kinds, and I think it's simply interesting to think about as we go forward, to think about potential connections between reward and homeostatic circuits. So I'll stop there and just say that everything I've told you about was done by other people. I'm just a mouthpiece, and these are the people who did that. Thank you. Mary.
I love that, but you know, you're not talking about what would happen if that system weren't functioning. It would be the other side of the coin, wouldn't it? Would the animal do anything?
So I'm not talking about what would happen if that wanting system were suppressed down.
Yeah.
And absolutely, as you say, it does suppress down on the wanting and things, that's right. Is that a converse sort of for a mechanism for overeating? Probably not.
I'm just thinking it's a really highly functional system.
It's a highly functional system that has functional consequences no matter what direction it's in. Yeah. I wouldn't invoke a suppression of that system as an anorexia type explanation, but there are other routes to that explanation. Yeah.
No, not anorexia,
Yeah.
but doing anything, getting out of bed in the morning.
Absolutely. Avolitional kinds of symptoms in lots of conditions beyond eating. Yeah. Yes. Oh,
Is there a connection with liking, wanting systems, and the ability to take the first cookie out of the bag and liking it, but then continuing to eat it all, even though it doesn't taste that great anymore?
I think it's such a major, excellent point in question, and yes, absolutely yes. What turns on this system normally? You know, we're putting amphetamine microinjections in the nucleus accumbens, but what actually causes dopamine and opioid release in the nucleus accumbens is taking the first cookie. So taking the first cookie is what's going to put the brain naturally in the state where now the cues are even more potent than they were before we took the first cookie. That's the natural mechanism, and it's a marvelous mechanism, but it can go awry. I should have, thank you for bringing that up.
So you talked a lot about what stimulates these systems, like the first cookie or an anticipation or an image or the piece of metal coming out. There must be a resolution, meaning, you know, some satisfaction, for lack of a better term. Could you speak a little bit to what you think that might be? Would it have anything to do with taste receptors? Would it have anything to do with postprandial metabolites and hormones acting on the peripheral nervous system? Hormonal changes after you eat? What do you think resolves this?
Well, I think all those things you mentioned would be excellent candidates for mechanisms that can push down on this system. And certainly this system, in moments of satiety, is pushed down on both the wanting and liking systems. It's the wanting system more even than the liking system. But the system itself almost needs to be pushed down on from those homeostatic cues because it doesn't have satiety built into it. It's a go system, both the wanting and liking system. They are go systems. And that's what they're meant to do. And it requires something like satiety cues to push them down. Even when they're pushed down on, it's hard to push them down entirely. The liking system, although it's spindly and hard to enhance, it's also hard to push down. We once did an experiment with super satiety, where we got rats to drink the equivalent of a couple of gallons of milk in a half an hour by just dribbling it into their mouth. And when they'd stop, we'd pause and then dribble it more until they drunk it. And then we'd infuse the sugar to see if they still liked it. And they still liked it. It was suppressed. The liking was down, but we could never switch it to negative. Even this grossly exaggerated satiety, super satiety state of the equivalent of 2 gallons of milk. So that may be one reason why palatable foods can still push through and make us have one more piece. It never goes to bitter negative.
I'm curious about what are the effects of exercise on this system, and are there other mechanisms that could, people go on diets that are historically unsuccessful, and do you have other suggestions for things to down-regulate the system?
I don't have a clear answer to how exercise is interacting with this system, although clearly, I mean, it is. Many studies by other labs have looked at this kind of interaction, but I think the answer is complicated. Maybe we could talk about that at lunch. Kevin, were you trying to? Oh, okay.
How do agonists increase eating behavior? So new agonists increase the demand of food. How does a dysphoric drug increase eating?
Yeah, I think that's a very good question. I mean, one way a dysphoric drug could increase feeding is through the hedonic self-medication route that George Koop draws on in drug addiction, and that Mary has also helped point out and shown actually works in eating disorders. Kappa agonists have kappa stimulation has mixed effects in different studies in food intake. Sometimes it suppresses it. So sometimes you don't need to eat for hedonic self-medication. You feel nasty, lousy, and you don't eat. But in other cases, it increases it too. So those would be the cases that.
Have you ever made the mistake of using both male and female rats?
We do use we do use male and female rats, and most of what I've said applies very similarly for both, with tiny, tiny modulations and intensities of certain things.
Kappa?
Let's talk about that.
I mean, a kappa antagonist, is there a difference in the sex? Is there a sex difference?
As far as I know, but you're telling me that I probably should know something I don't, so.
So these data, from what I could gather, are from sugar. What about artificial sweeteners, which are generally perceived as more bitter? So I would think would inhibit the kind of pleasure systems in the brain, and yet there is evidence to show that people who eat diet foods tend to compensate for the lack of calories and eat more.
Absolutely, and that's a good point. Yes, the rats are very sensitive to taste, and they don't like some of the artificial sweeteners nearly as much as sugar. But you can sort of mix it with a little sugar and mix it with other things, the artificial sweeteners, and then they like that too. If it's a taste they like, then what I've said, I think, those tastes tap into the same mechanisms. This increases in the liking mechanism will make any liked thing liked more in that way. The mixed palatability of the artificial sweeteners to begin with, especially to the rats, some of which just won't ingest it unless you mix it with other things. That's, tapping in a entirely different sort of mechanism, and maybe people respond to that too. The overcompensation of eating is probably entirely separate. That's sort of learned, as I think, as Suzanne Higgs, Terry Polly and someone helped me at Purdue have kind of shown that there's a gradual sort of Pavlovian learning that diluted calories, when you mix in the artificial nutrients, the rats learn to overcompensate, and that's a mechanism that would be interesting for these, but it's separate. Yes?
You established that stress can mimic the dopamine stimulus. It's possible that this, because normally the obese person is normally with a lot of high stress. Can this mimic effect compensate the reduction of the dopamine receptors?
I think that's a marvelous question. I don't think we really know the answer to it, how real stress states are interacting with these systems. I think most, sort of, as research goes, we focus on simple notions, and mostly one at a time. The CRF, hedonic self-modification, and then this, and what we need to do is look in real stress, how multiple systems are being impacted and how, which wins. Yeah. I'm not sure who was first, I'm sorry.
Just a question. So what is your opinion, given the similarities with the addiction circuitry and drug addiction, and what we know about treatments for drug addiction and pharmacology? Do you think that there's any hope that there will be medications that will help it?
I think we're a long way from effective medications that can tap into this system, at least for drug addiction that could reverse sensitization changes but not have all kinds of unwanted side effects. We're a long way. I think the best therapies are still kind of cognitive behavioral sorts of therapies and learning to accept the cravings and things. But in principle, it could happen that a medication could. It's just not in our career lifetime, probably.
I'm interested in the ontogeny of the effect in terms of when you get exposed versus when these preferences develop. You know about sucrase, the stuff that you put on babies' tongues at the time of circumcision, which has an opiatergic effect. That's basically your, infodopia. We know from Michael Pollan's work that the earlier you give your kid your birthday cake, the more they're going to want later. There's some data in terms of animals, in terms of the time of when they first sense it versus when they're going to want more. Does your data give us any information on when these phenomena develop and what we could potentially do to maybe push it back?
I think that's a marvelously important issue, of course, for modern society and clinical issues of obesity, how early life experiences change. I would never want to argue against giving sweet taste at the moment of circumcision. Life is hard enough, and I don't have data that bears on it. But people like Julie Manella and others at the Monell Chemical Senses and such are, I think, studying how in more clinically relevant situations to overeating, how even beginning prenatally, but then in postnatal experiences may influence later preferences and overeating patterns in ways that key into these systems. Maybe one more, Diane?
I'll just say, preview of coming attraction, I'll speak a tiny bit about that at 9 o'clock right after lunch.
Great. Thank you, Diane. Thank you so much.